Hey everyone, thanks for joining us. Today's conversation will be in one of our favorite areas, cosmology, talking about, some of the great achievements, some of the remaining mysteries, probably dark matter, dark energy, things of that sort will be part of the material we'll cover. And I'm so thrilled that we have really one of the great young leaders of the field. That's Hiranya Peiris, who is the 1909 professor of astrophysics at the University of Cambridge. And I think I'm correct in saying that she is the first woman to hold this chair in 115 years, which is absolutely wonderful. And she holds this chair because of the great contributions that she has made and is continuing to make to cosmology. So Hiranya, welcome to our conversation. Thanks so much for joining us.
Thank you so much, Brian. It's really wonderful to see you again, and I'm really thrilled to talk to you.
Absolutely. And I was thinking, as I was walking over here this morning, and I could be wrong, and correct me if I'm wrong, of course, but could it be that the last time we had a conversation was at the University of California, Santa Barbara in like 2003 or something like that?
I think that's right. I think that it was the post-WMAP conference at the KITP, which was a very exciting time.
Yeah, so perhaps I'll just jump in with the following question, given that is the last conversation we've had. So when you go back 20 years to your younger self and you think about where you imagine cosmology might be 20 years later or 22 years later in the year 2025, how have we done?
I think that we have done extremely well on the perspective of actually probing the universe with data. And I think it's exceeded my expectations in terms of the different epochs in the history of the universe from which we have observations. And we have pieced together a story of the universe that spans nearly 14 billion years of cosmic time. What has disappointed me, however, is that we have discovered all of these mysterious components of the universe, and we are no closer, I think, from 20 years ago in understanding how this information from the very largest scales we can observe actually connect to the physics that we can describe at the very smallest scales, the microphysical picture. So that juxtaposition is very interesting to me. And so cosmology is at a very strange time right now, where we are drowning in data and we can't explain it in terms of fundamental physics very well.
Now, just to give the audience a sense, the fact that you can say those words, drowning in data, when we're talking about cosmology, this is not in any way, shape, or form the way the history of the subject always has been, right? I mean, in the earlier days, you would have probably said something radically different from that, right?
Absolutely. If we go back 40 years or even 30 years, we would have said completely the opposite thing. There were many, many theories and very, very little data to constrain them. So it was a playground for theorists. People had fabulous ideas about what the origin and the composition of the universe could be. Many of those theories have actually been ruled out by the data that we have now. So it's gone from a very speculative field to being a very data-rich field. And as we have narrowed down the theories that could fit the data we see, we are left with just a handful of possibilities from the ideas that were around even when I was a PhD student.
And so would you say, when you assess the field, and then we'll turn to getting into some of the details of the mysteries and your own work and so forth, but when you assess the field as a whole, would you say that the theorists have yet to be sufficiently creative to come up with the right ideas? I mean, the fact that we have a few remaining ideas, is that because we're so good and so smart and we've been able to cull the rich class of possibilities all the way down, or have we just not been creative enough to put forward perhaps the ideas that would take us to the next level of understanding?
I don't think it is a challenge in creativity in the sense that there were very, very creative proposals put forward. However, when we measure the few numbers that we can actually get from the sky that constrain these theories, what's left is a sort of vanilla version of the original, very creative, highly elaborate proposals, in the sense that the numbers we have don't really point to a microphysical fundamental understanding that we can look at and say, that's the answer. So it's definitely not a challenge in creativity. It's just that the universe happens to fit a phenomenological picture which reveal huge puzzles in fundamental physics, and we don't have any smoking gun to point us towards a particular theory direction to go in.
So when you say phenomenological picture, and I think that is how I would describe our current state of understanding as well, but maybe just for the audience, what does that mean to you?
Yeah, so what it means to me is that, so we have rich data sets that we fit with a model that's phenomenological, that's constructed under the assumption essentially that general relativity is correct. And that leads to solutions for the expansion of the universe over time and how structure grows within it. And so there are ingredients that go into the prediction for the data that comes from postulating such a model. And the ingredients that we have found to fit the data includes, dark matter and dark energy. Dark matter, at least there are many theoretical proposals that are plausible. Dark energy is a word we give to a phenomenon that we just don't understand, which is leading the expansion of the universe to accelerate over time. And also, there has to be a primordial origin for all of the structure we see in the universe. Our description of that is at the level of a toy model. I think that we have seen some very non-trivial observations that narrow down the field, as I said before, but these three different ingredients, they're like, three tooth fairies when you're maybe allowed one to be part of a model. And so that's what I call phenomenological. We can describe how these ingredients affect the observables that we measure, but there's no actual fundamental microphysical understanding of what those phenomenological components mean.
Now, oftentimes cosmologists speak of parameterizing the data using 6 numbers, right? Mm-hmm. So you've named a few of the parameters that go in. The others are a little bit technical, but perhaps you can just give a nodding reference to what the other parameters are.
Okay, so rather than listing the parameters, we could just talk about, what constitutes a cosmological model. So first you need to postulate some form of the primordial fluctuations. So that's an amplitude, and that is a scale dependence, like at each wavelength, how much power you have. So those are 2 numbers. And then we have to describe the geometry of the universe. And the geometry could be flat or open or closed spatially. And once we fix it to be flat, which is observationally motivated as well, so we have tested that assumption, that essentially gives a class of cosmological models that you can go on to look at the ingredients of. And then that set of ingredients are baryons, which is all of the stuff that we see around us in the universe, everything that interacts with light, the physics we test in the laboratory, in the Large Hadron Collider, all of that is baryons to astronomers. That's only 5% of the energy budget of the universe. The rest of it, the 95%, is dark matter and dark energy, mostly dark energy. But dark matter outweighs ordinary matter by a factor of 5 to 1. And so that is a very confusing picture. And on top of that, we can also measure when the first stars formed. So that kind of completes the set of 6 numbers that we talk about.
And I mean, how remarkable is it that effectively all observations, broadly defined, can be at least described in this phenomenological model that you made reference to using just 6 dials, 6 dials, you turn them and you're able to, in some sense, understand the observations. Is that shocking? Is that remarkable?
Well, I think it's truly remarkable because Originally, at least, this set of 6 numbers came from looking at the cosmic microwave background, which is the earliest, most ancient light that we can see in the universe. So when we fit to the cosmic microwave background, it's not just that we have these 6 dials. We can actually postulate many other dials that suggest many different deviations from this 6-parameter model. And we can test those also. And we find that those other dials are not necessary, more or less. And then we can do a consistency check. We can push this model forward in time from the very earliest times to now. And we can make predictions for how the universe would evolve under the assumption of those 6 dials. And every time we've done that consistency check, it passes at quite remarkable levels. There are inconsistencies that I'm sure that you will bring up later, but those are at quite small levels compared to the whole qualitative picture, which seems to make sense and hold together. So that's why we take this phenomenological picture seriously enough to then start to talk about what is the fundamental physics that we don't understand yet.
Right. Now, you also made reference to the underlying model, which most cosmologists, I think, today still focus on the inflationary theory as sort of the dominant paradigm. You called it a toy model.
Yes.
And I wonder, do you think that some of the founders of the theory would take offense at that, or do they agree? Would they agree that it's sort of in a rudimentary early stage as opposed to a mature final cosmological description of the universe?
I definitely think they would agree. Maybe the word toy is not what they would use, but they probably would agree that it is not the final answer that explains everything. Inflation postulates physics at a much, much higher energy scale than what we can test in the laboratory. It is an extrapolation of fundamental physics, order many, many orders of magnitude. So I think it would take a very brave person to say we know everything about the physics that takes place at such high energy scales. However, I think inflation, even as a toy model, as a paradigm, has made very non-trivial predictions that have been observationally confirmed. The favorite one that I have, which makes me, as a more observationally inclined person, to take inflation seriously, is that it predicted super-horizon fluctuations. And when we measured the correlation at very large angular scales between the temperature and the polarization of the cosmic microwave background in WMAP all the way back in 2003, we saw direct evidence for super-horizon fluctuations. This, at a fell swoop, ruled out a lot of theories for the causal origin of cosmic structure. And so for me, that is a really non-trivial piece of information that we now have about primordial physics.
And again, just
yes.
for the audience, maybe just superhorizon may not be a familiar term for everybody. Maybe just give us a quick sense of what that means.
Sure. So when we take the size of the observable universe and we push it further back in time, I said earlier it's been expanding over time. So at earlier times, that observable region was smaller and smaller and smaller, right? So if you look at the cosmic microwave background, it comes from a time when the universe was only about 380,000 years old. Now it's 13.7 billion years old. So this is like a baby picture of the universe. And if you look at the universe at that time in the cosmic microwave background light, we see very tiny variations in the temperature of the background, which correspond to very tiny deviations in the density of the universe at that time from place to place, at about 1 part in 100,000. So if you look at the universe today at very evolved times, you can see the universe is very inhomogeneous. We are sitting on a planet that's extremely dense. Out there in space, the number of hydrogen atoms in very large volumes will be very tiny. It's very inhomogeneous in the vacuum of space compared to us, right? So why was this early universe so uniform? That requires an explanation. And one possible explanation of that uniformity could be a causal explanation. There's some physics that can communicate just at the speed of light and make everything in that observable volume back then the same from different places. However, inflation postulates that actually it's an acausal mechanism that created that structure. In other words, the early universe expanded much, much faster than the speed of light. This often strikes confusion when you talk to people who haven't studied general relativity, because we've all learned that light has a speed limit and it is the ultimate speed limit, and you can't communicate faster than light, and that is absolutely right. But space-time can actually expand faster than light. So by superhorizon, it basically means that the horizon that inflation creates will be much larger than the one that you would naively expect under this causal picture where everything just operates at the speed of light.
And just for clarity, even though you use the word acausal, it's still causal. It's just that inflation makes it appear as though it would be acausal because the places are so far apart that using naive speed of light calculations, they would be beyond each other's cosmic horizon, the distance that light could travel since the time of the Big Bang.
That's a perfect way of putting it.
So that's great evidence, as you note, in favor of the inflationary picture. But as you also mentioned, it's more just a paradigm as opposed to the final proposal for how things are constructed in our universe. And so I thought it'd be good now to dig in a little bit more deeply, especially on issues that you've spent some time thinking about, like dark matter. So, I think most in our audience are certainly familiar with the notion of dark matter, that it was introduced all the way back in the 1930s, people like Fritz Zwicky and then Vera Rubin, from the motion of galaxies and stars and galaxies, inferring that there had to be more stuff than light revealed. Otherwise, stars should be being flung outwards from rapidly rotating galaxies and so forth. So, given that as background, where would you say we are in our level of confidence that dark matter is real and not just a dial in a cosmological toy model that we use to model data?
Absolutely. So from a phenomenological point of view, in terms of probing its gravitational interactions, I think that dark matter is very real, and we have evidence for it. You mentioned a few of those, for example, galactic rotation curves. So this is dynamical evidence for dark matter. If you look at clusters of galaxies, we can directly see the effect of lensing. The dark matter in clusters of galaxies gravitationally lenses distant galaxies in the background, and we can see exactly what we expect from the presence of dark matter. There is the so-called bullet cluster, which also shows that where we see gravitational lensing is not where we see ordinary matter. So it's not like some kind of weird ordinary matter that we don't know about that is causing that lensing effect. We can see it in the weak gravitational lensing of galaxies. And we can definitely see it in a more phenomenological sense, but in a very real sense, in how we describe the cosmic microwave background power spectrum, where if we didn't have dark matter, our prediction for that would be extremely different. So observationally, it seems very, very solid to me that there is a type of matter that we can't see. The alternative could be that, actually, I said right at the start that we have general relativity underlying our cosmological model as an assumption. And maybe general relativity isn't right, and there's some different theory of gravity that somehow naturally predicts the existence of some other phenomenon which we would wrongly interpret as dark matter. So many physicists have been pursuing those ideas, and I think that many of these observations that are very naturally explained by the presence of a type of matter that we can't see through normal electromagnetic interactions, that idea is a much more natural explanation for our observations than these other theories, where you have to literally turn upside down and dance a jig in order to try to even explain part of that set of observations. So it seems to me that this phenomenon is not going to go away. We just need to explain it in terms of fundamental physics. And I personally think it's a particle.
And can you imagine any upcoming observation or experiment that would cause you to change your mind on dark matter?
Probably not. Yes, if you can come up with some experiment that can exclude both the WMAP hypothesis and the AXION hypothesis, completely, perhaps I would start to wonder. But currently we are in the middle of an investigation to these very compelling classes of dark matter candidate particles, and I'm personally on one side of that investigation. I'm very much interested in studying the AXION hypothesis and trying to constrain that both with cosmological data but also in the laboratory. Many large collaborations of physicists are going after the WMAP hypothesis. So yeah, if both of these ideas are shown to fail, I think it is very motivated then to start to think twice about what we could be seeing. But currently, I don't foresee an experiment that would make me change my mind on this.
So let's jump into those two classes. My very first paper as a graduate student was a dark matter candidate, which falls into the WMAP category, weakly interacting massive particles, for people who don't know the acronyms. Let's start there. And I can tell you what impresses me the most, and I think many people share this view, but I wonder if it's also what compelled you to at least take it seriously. The idea of the dark matter being one of these weakly interactive massive particles, the WMAP idea did not emerge as a solution to the dark matter problem. It emerged to a whole different problem in particle physics that we could spend a little time talking about, called the hierarchy problem. But you try to solve one problem in particle physics, and you do so by introducing various kinds of symmetries which yield this kind of weakly interacting massive particle. And then as a byproduct of solving that problem in particle physics, you seem to solve the dark matter problem. That, to me, made it almost seem like this has to be true, right? It almost is too beautiful to be wrong. A generation behind me, was that your experience learning about this as well?
Absolutely. I think this is also true for the AXION set of ideas as well. I really find it very compelling for both WMAPs and AXIONs that they were not invented as a just so model to fit a hole in cosmology. They instead arose from completely different and fundamental considerations in particle physics, and the hierarchy problem on one hand, the strong CP problem on the other. And so, you try to follow fundamental considerations to try to explain a phenomenon in particle physics, and then out of that, a particle arises naturally, and at least in the early days for the WMAP case, naturally explains the abundance of the dark matter in the universe. I think that that scenario has actually possibly gone away now for WIMPs. However, those motivations which are not like, let's invent a particle to fix a problem in cosmology. That's why I really highlighted those two categories. There are also many candidates for dark matter that seem to be motivated just by, oh, here's a new idea for dark matter. And I find those kinds of approaches to try to explain dark matter to be less motivated, because you don't want to invent something to fit a hole. You want to think things through from a fundamental perspective and see whether the overall picture about our understanding of particle physics and cosmology hangs together. And in the case of these two candidates, it really does.
Yeah. And so we'll go to AXIONS in just a moment, because I know that you are working on that directly. But just to give our viewers a sense, people have been looking through experiments, observations, for these WIMP dark matter candidates for I don't know how many years, but a lot of years, right? It's probably 40 years or so, something on the order of that.
Yes.
There have been hints now and then. None of them seem to have really become consensus. I think the general view is that we certainly have not found the WIMP dark matter. So at what point do you say, it was a great looking idea on paper, but it's just not something that nature seems to have made use of?
Yeah, I think that we will get to a floor that is set by experimental considerations after the next set of WIMP experiments. And that is probably when we should call it a day with the WIMPs. But I think there's still some discovery space left. And so I personally believe we should actually completely test the hypothesis. The fact that somebody didn't find something for 40 years in fundamental physics, I don't think really matters as much as here is a theoretical idea that's very well motivated. We need to exclude it completely to say that it's dead. I mean, just taking a completely different experimental scenario, people were measuring noise in gravitational wave observatories for 40 years before they found them. We are pitting our wits against the entire universe. I mean, it's a very audacious undertaking. Like, you don't expect to make discoveries like this and that. However, what I think is true, and I don't know if you agree with me, is that the original part of the parameter space of the WIMP hypothesis, which would have naturally explained both the hierarchy problem and predicted the observed abundance of dark matter, that's already been excluded. So from that perspective, it no longer quite, solves the problem and, gives you the dark matter at the same time. So from my perspective, that's why I personally don't work so much on that hypothesis.
Yeah, no, the WIMP idea is, of course, under serious pressure. And I think you're right. Within a small number of years, maybe we'll find it, which would be, earth-shattering. But if we don't, we probably do need to retire that particular idea. And as you mentioned, there is a second idea, which I guess, in terms of crediting WIMPs, it's really hard. There's so many people who are involved in that idea, from supersymmetry and things of that sort. But for AXIONS, I guess it's really, Steve Weinberg and Frank Wilczek and probably others that I'm leaving out, so it's always dangerous to give credit. But it's a somewhat more difficult problem to talk through, the strong CP problem. Maybe speaking in terms of the observations of the neutron's electric dipole moment, how would you try to explain the whole in particle physics that this idea was meant to solve, and then as a byproduct giving a dark matter candidate?
I probably wouldn't explain it in terms of particle physics, because it'll be like extremely confusing. But I do find that the explanation in terms of the neutron electric dipole moment actually helps people understand it. So there's a number in the standard model of particle physics, which is the so-called neutron electric dipole moment. And this number is not predicted by theory. It could have taken any value. And when you try to measure it observationally or experimentally, you find that the number is extremely small. I think it's like something like 10 to the minus 10. Correct me if I'm wrong. So this number being so close to zero was a surprise. It could be a number which is of order 1 and instead it's tiny. So, physicists don't like fine-tuning. So people tried to postulate a dynamical mechanism to make this number naturally go very close to zero. And so that was the explanation for the so-called strong CP problem. But then Frank Wilczek and others noticed that, if you solve the problem that way, out pops a particle, which they call the axion. Axion actually is a type of detergent, I believe, and it was meant to wash away the sins of the standard model of particle physics. And Frank shows this wonderful picture of the actual box of this detergent. I've never seen one in person myself. Maybe it doesn't exist anymore. But that was the origin of the axion. The subsequent years have seen variations on the theme of axions. It's different from the WMAPs, right? It's got wave-like properties as well as particle-like properties, which means that the way that you would try to detect it in the lab is very different. And people also postulated ultralight versions of this axion, which doesn't necessarily go towards the original motivation for axions, but it does allow a very, very, very large range, like orders of magnitude in mass over which the particle can exist, which means that it can be quite challenging to experimentally test in comparison to the WMAPs. And it also is the case that the experimental technologies that are required to detect the axion are much more challenging. And so it has been a much harder type of dark matter candidate to try to detect in the lab, and even to test cosmologically, which the very, very small mass versions of these axions, the ultralight axions, they leave a signature in the sky, and we can try to test it there. So there are possibilities, but when you have a particle varying in mass over 20 orders of magnitude almost, where do you look, right? Any experiment you can build will only scan over a tiny fraction of that allowed range. And so you could probably say, if you can't predict the mass over such a large range, then perhaps it's less compelling. But we can have that discussion. However, I think it is very well motivated, especially the QCD axion. So that's what I would like to see tested in the laboratory. And
is
I'm
that
part of one experiment.
And you are part of an experiment doing that, if I understand. Is that right?
Yeah. So do you want me to talk a little bit about
why not?
the
Yeah, I mean, how do you,
Okay.
I mean, I guess people just on the WMAP front, people have set up more standard detectors, really trying to catch one of these particles as they waft through the detector. But I gather the strategy that you're taking is quite different from that.
Yeah, that's right. So we try to use the wave-like nature of the axion to try to catch it. So there's a very, very, very tiny probability of an axion decaying into 2 photons, right? So the probability is so low that if you were trying to just catch one of these decays in the act, you would have to wait for several lifetimes of the universe, which, we are not patient enough to do that. So what you instead try to do is to stimulate the decay by putting a cavity in a very, very strong magnetic field to stimulate decay. And at this point, the axion field, if it exists, will be acting like a classical field. Okay, so there are many, many axions in this cavity, and that boosts the decay probability to a sufficient number that it's still very, very tiny, but we might be able to detect it after observing for a small number of years, like 4 years or something like that. So what you do is basically try to match the resonance frequency of the cavity to the wavelength of the axion mass you would like to detect. And this immediately hopefully tells you that if you have a box in which you're trying to catch the axion and the wavelength has to be the size of the box, that you can only scan over a very narrow range in mass. And I said earlier, one of the challenges is that the mass range is very large. So our experiment actually broke that connection between the geometry of the cavity and the wavelength by introducing a resonator that was made up of what is called the wire metamaterial, which means that what matters is the plasma frequency of this metamaterial rather than the geometry of the cavity in terms of matching it to the axion wavelength. So our experiment can tune, and furthermore, it allows you to actually test the prime parameter space of the so-called post-inflation QCD axion, which is one of the most motivated ranges in parameter space.
So basically, and again, correct me if this is a wrong metaphor, but it's as if you have an axion radio and you're able to tune the frequency at which it would be able to broadcast, and using this clever technique of these metamaterials, you're able to tune those wavelengths over a much wider range than you would have ordinarily thought.
Yeah, that's a perfect analogy. In fact, I think one of the experiments, not ours, is called the dark matter radio. So
is that right? Did not know that.
Yeah. People actually do use that metaphor, indeed. So the radio. Imagine the radio had just one station on it, and you didn't know where in the frequency range you can scan over this station was, right? So where would you build the range of dial tuning that you can do? Probably most people listening to this interview don't even know that you can tune a dial in a radio anymore. I don't know whether that's a thing. I haven't owned a radio for a long time.
It's too old a metaphor, you're saying?
Yeah, it's too old a metaphor, maybe. Right. However, it's like you don't know where to find the station, so you have to tune. And so we've built a type of radio where you can tune in the part of the frequency range where physicists think the particle is most likely to exist.
Right.
So that is very exciting. So this experiment is currently being built at Yale. And
what sort of a team? I mean, is this particle physicists or more of the condensed matter or both? I mean,
No. So they're particle physicists, but they are people that are not necessarily from the same community that do the WMAP experiments. It actually has very close connections to the technology that you would use for the cosmic microwave background. The microwave receivers that you build in the cosmic microwave background, the signal that we are trying to read out, the readout technologies have very much in common. So it's a different community, but they're still particle physicists. They tend to be very specialized in doing these axion experiments. So in our team, actually, no, it's a tabletop experiment, right? It's not like a gigantic international collaboration. It's more the size of, WMAP, So it's really nice to work in a small team where everybody has a role and everybody contributes and they have a commitment to the project. So that's been very nice.
And so was your history, and I probably should have mentioned it early on, that were you David Spergel's student? Am I getting, is that wrong?
Yes, I was, yes.
Yeah, so we had David on this series of conversations not too long ago, talking, of course, about WMAP. So our audience should know that you were part of that team. But has that experience informed what you're doing in this axion search?
Not directly. So let me give you a little bit of history about where this axion experiment idea came from. Before I was in Cambridge, I was the director of a center in Stockholm, which was basically the mission of that center was to stimulate collaborations and conversations and exchange between cosmologists, particle physicists, and astronomers. And Frank Wilczek actually spent quite a lot of time in Stockholm. And so he also had postdocs working with him. And two of those postdocs and Frank came up with this idea for tuning using wire metamaterials, taking the limitation of these cavity experiments and removing it with this idea. So as you know, I'm not an experimentalist that works in the laboratory, but as the director, my role was to kind of try to stimulate a actual version of this experiment to be built. And the idea attracted huge attention because it was so cool. And we were able to provide seed funding to actually validate the concept to the point that we could propose it as a full-scale experiment. And one of the people that was also in the Stockholm community was Jon Gudmundsson, who might be known to some of your viewers as a cosmic microwave background experimentalist, who had actually done his PhD also in Princeton and been trained by the Princeton group to do CMB work. And he brought his CMB experiment expertise and translated it into the technologies that we use now for these wire metamaterial resonators.
And so where are you in the experiment then? Is it underway or?
So it's currently at the stage where we are setting up the magnet. So I mentioned that there has to be a very high field magnet. We inherited the magnet from a previous experiment in Yale, but now we are in the process of actually not using that, but actually building a bespoke magnet for this experiment. We are also in the R&D phase of actually selecting what is the style of resonator and what exact tuning mechanism we would use. So once those selections are made and the magnet is in place, we would start data taking, probably in another couple of years or so. So the lifetime of the experiment is more like 6 years to actually probe a prime part of the parameter space. We of course want to go deeper and more sensitive, and that would probably require a superconducting version of this this experiment. Currently the resonator, I should have brought it actually, it's in my office, but I don't have it with me. The resonator is literally, you can hold it in your hand, it's small, and it's a tabletop experiment literally that fits in a university lab. So it's got just like a bunch of wires, and you can do many things with these wires to actually try to enable tuning by literally changing the spacing between the wires. But there's many ways to do that. And you can also have the consideration that, this experiment, once it's put into the cavity in the magnet, and the whole thing is cooled down, you don't want lots of mechanical things going on in there, shaking things up and making vibrations and changing temperature. So you want to minimize the mechanical the mechanism that you would use to tune mechanically. So those are the investigations we are doing now, but it goes at a very fast pace.
And what's the mass range for the AXION that you'll be able to potentially be sensitive to?
Yeah, so it's basically this 10 to 20 gigahertz range, which is currently decided to be the prime kind of real estate in terms of the post-inflation QCD AXION. So recently, I think possibly motivated by the fact that these experimental searches are starting up, theories are starting to refine their calculations. For example, Ben Safdie at Berkeley is working on this. Basically, the calculation is feasible, which is not true for many theoretical proposals. It's feasible, but it's challenging. It involves doing lattice simulations of cosmic string decay following inflation. And there is possibly some hint, theoretically, out of these numerical studies, that the masses are actually a bit higher than that 10 to 20 gigahertz range. And so, the next version of this experiment would probably be designed to push even higher. And there are experimental ideas to do that. So it will be feasible.
I see. This is all incredibly exciting. So this has been so far on the more sort of particle physics, if you will, end of things, WMPs, QCD, AXIONS, and various generalizations thereof. You're also working on the observational front, right? Aren't you also part of the Vera Rubin telescope?
Absolutely,
as well?
yeah. So most of my work, actually, these are side projects
Right.
that I mentioned.
Yeah.
So most of my work actually is on, I moved on kind of from working on the cosmic microwave background to working with very, very large galaxy surveys to probe the more recent universe, partly from kind of my journey as a researcher that was motivated by, yes, we built a model based on this very early epoch of the universe. Now I want to test it in the late time universe. So that's my personal motivation for kind of slightly changing direction in my focus. So I'm very excited by the coming Rubin data. So literally a couple of weeks ago, we got the first photons on the LSST camera. Sorry, LSST is the Legacy Survey of Space and Time. This is what will be conducted by the Vera C. Rubin Observatory, which is a huge, wonderful observational facility, which is in Chile.
And have you gone down? Have you gone down to Chile?
Yes, I have. I managed to actually get to visit it in December 2023. It was so cool because I've been part of this experiment since. Cosmologists call observatories experiments. Forgive me. It's really an observatory. It's there to observe the universe. So I was hooked by the concept of Rubin, and I joined the project in 2013, I think. And in December 2023, I managed to actually go to the summit and see the construction project. It was just before Christmas. So we basically got the whole thing to ourselves and we got a fantastic tour. The thing is enormous. It's like a huge machine, and it's more like visiting the LHC and seeing those huge experiments to see this amazing purpose-built telescope mount. So now the camera has actually been installed in there. The camera is the size of about a truck. It's the biggest digital camera ever built. And it will observe the sky. So it'll take pictures of the southern sky, the entire southern sky roughly every 3 days, and do that for 10 years. So it'll make a picture of the universe that is varying in time, which is a movie, right? We stitch together images to make movies. And so basically that's the concept. So a movie of the universe. And let me tell you the level of advance that this project is. Your viewers might have heard about the Sloan Digital Sky Survey, which was a milestone in observing the sky with this automated, digitized survey modes. So that took data for 20 years. And the depth reached by each of these sky scans every 3 days by Rubin equals the full 20-year depth of the Sloan Digital Sky Survey.
Wow.
It's like mind-boggling.
Yeah.
And so this observing mode of getting very deep data over a very wide, part of the sky, but also very rapidly, this has never been done before. And it's this discovery space that really excites me, because every time we've looked at the sky in new ways, we find new things.
So you're saying, just to emphasize that crazy data point you gave us, every 3 days is equivalent of the LSST is equivalent to 20 years of the Sloan Digital Sky
That's right.
Survey. Wow.
Yes.
And so, when you hear data of that magnitude, especially in this era where we have AI systems that are being built to handle or really to leverage big data sets. Is AI an important part of how you will go about analyzing that data, or what? Maybe we'll say it differently. What role, if any, will AI have in trying to make sense of this amount of data?
It'll have a huge role. It'll have a huge role. It has to. I mean, my personal work towards actually analyzing the data is very, very reliant on something called generative AI, specifically diffusion modeling, if you've heard about that. But there are many, many different ways to actually leverage AI into our analysis. One is simply classification. So let me explain this. So, every night we will get 10 million alerts telling us something is changing in the sky, right? Okay, well, most of those changes will not be interesting, but there could be very rare and extremely valuable sources that you want to then point follow-up instruments at and take spectra or take more observations, while Rubin will have moved on, right? How do you look at the needle in this haystack every night? Humans can't do that. There's no way. Like, we could hire all of the graduate students in the universe and we could not do that. But we can create filters saying we want to look at things that match this set of criteria, or we want to look at objects that don't match any known classes of objects. And we can implement those filters to run live. And usually these leverage classification algorithms that are machine learning algorithms. Because we don't have principled physics models for the sources necessarily, we have to use a data-driven approach to actually construct our models of what these sources will be and how to pull out the ones we want to look at, and how to look at unusual sources or rare sources. And so that is one context in which we just could not do it without machine learning.
And so will you be sort of waiting for the bells to go off when, for instance, the alert is, this is something we have no idea how to classify because we've never seen anything like it, and then you jump on that? I mean, is that really the moment that you're waiting for in the next months or years?
Yes. So I also have sources which are very rare that I really care about, that I would also jump at, not just the unknowns. Yeah. So there are sources we've never seen before. There are sources which are very, very rare. And let me give you a couple of examples. So you probably know that there is one source known, which is a gravitational wave compact object merger, a merger of neutron stars that also had emitted an electromagnetic counterpart.
You mean GW17817 or something like that?
Okay, yes, that is what I mean.
Right.
So you know the telephone number; it is very famous,
Although I probably got the number wrong, I should say.
No, GW170817. You're perfectly right.
All right.
So that had an electromagnetic counterpart, which has an astronomical telegram number, which I can't even remember. There's a name for the counterpart as well, which is a telephone number. Anyway. This one source and the coincidence of the gravitational wave and electromagnetic observations revealed a huge wealth of information about, for example, our process elements in the universe, where gold is made in the universe, and also weeded out theories of modified gravity over something like 10 orders of magnitude in a parameter that matters in terms of classifying such theories. So we know of one such object. The last one was, back in 2017. Rubin is
I should ask. I don't follow that in detail. So there has not been another example of a merger that had an electromagnetic counterpart.
No.
Okay.
That's right. But Rubin is the perfect instrument for actually discovering these counterparts. So that's one of those. That's
a filter you've got in there, and wow, yeah.
That's right. So my team and I have been constructing models of what the electromagnetic emission would look like from populations of such sources, right? We can't just use the one known source, because if you look for exactly the one you've seen before, you probably will miss a lot of sources that are from the population, but not exactly like that one. So yeah, so that's one example of a rare source. Another one is...
And before you go on, Hiranya, just let's say you were able to find another or a dozen other of that variety. What would you be able to do with that? Can you imagine what it will lead to?
Oh, absolutely. So the reason I got interested in this, do you want to talk about the Hubble tension? Because it's related to that.
Yeah.
Okay. So so I mentioned right at the beginning that the universe is expanding. This is the most fundamental fact about the universe, the fact that it's expanding. And we can, make measurements in the cosmic microwave background and predict what the current expansion rate of the universe would be. This is called the Hubble constant. So that's a prediction of data that was fitted at a time when the universe was a baby, right? And now it's an adult, and we want to see how fast it has grown. So we can try to measure this expansion rate at late times, and there's a method called the distance ladder, which actually allows you to do that measurement. And guess what? The numbers are different. One is about 68, one is about 73, and they differ by what physicists call 5 or 6 sigma, which is quite a substantial statistical difference. And this is called the Hubble tension, and it hasn't gone away despite about a decade of debate now. And people have refined their analyses on both sides, the early universe side and the distance ladder method. And despite a huge amount of work, the tension hasn't gone away.
And before you go on to the next step, I should just remind our audience, just for people who are regular viewers, we've had on this program talking about that Adam Rees and Wendy Friedman. So those are 2 really good examples to have in mind. We've had Alex Filipenko, we had David Spergel, we had Lyman Page. So we've had a whole variety of perspectives fleshing out this Hubble tension, but you're right, we ultimately at this stage come to a place of there's a real difference between early universe and late universe measurements or predicted measurements of the expansion rate, and we don't exactly know what to do. And so I gather you're going to give us some potential way of using these mergers to gain insight.
Absolutely. So the problem with the distance ladder method is that you have to start locally, like in the neighborhood of our Milky Way, and measure distances and redshifts out to further and further distances from us. And you can't do that in one fell swoop. You have to do it in different rungs of the distance ladder. And at each rung, astrophysical complexities come into the picture. And there are always debates about, is it new physics, or is there some astrophysical systematic that we don't understand? And
but just to be concrete, can you just remind us of a couple of the early rungs, maybe Cepheids and Type 1As and so on? Yeah.
So the first thing is Cepheids. So it's actually a really good time to talk about it, because it's been about 100 years since we knew that there were other galaxies out there, right? So I believe it was October 1923 that Hubble detected a Cepheid out in the Andromeda galaxy, which is we now know is the nearest big galaxy to the Milky Way. But at that time, they didn't know that it was an external galaxy. And the key evidence came from measuring this variable star called Cepheid. And Henrietta Swan Leavitt, who was also a brilliant astronomer, had worked out that there was a relationship between the luminosity and the period of this kind of pulsating star. And if you could measure its period, you knew its luminosity, its brightness.
Absolute brightness. Yeah.
Absolute brightness. Yeah. And then something's absolute brightness, and you see it at its apparent brightness, and you know its period, so you can actually then work out how far away it is, right? And we can also measure distances to the lowest rung by the method of parallaxes as well. So we can measure Cepheids in our Milky Way, we can measure them in the Large Magellanic Cloud, and also in some distant galaxies. And these stars are not bright enough to be seen way out in the distant universe. So there you have to use a type of standard candle, which is called a type 1a supernovae. And so this is a class of exploding star, which are much, much brighter. They can be brighter than their entire host galaxy. So we can see them further out. And so you have those two types of standard or standardizable candles. And if you can measure in an intermediate regime, in some galaxies where you have both Cepheids that you can see and type 1a supernovae going off, then you've got a connection between those two rungs, and then you can connect things up. So those are examples of different rungs. There are other more complicated ones that I won't go into. But the key here is working out distances to objects and also their redshift, okay? So because there are all these rungs, and you know, Wendy Friedman has another type of rung that she's working on, which bypasses some astrophysical uncertainties that are in the original way of doing this distance ladder. So there are many astrophysical ways that you could try to construct rungs. I personally feel that all of these rungs will have astrophysical uncertainties associated with them always. And so therefore, I would like to see a sample of gravitational wave standard sirens. And so let me explain what that is. If you are able to basically, you know, get a sample of about 50 of these objects where you have both the gravitational wave detection and an electromagnetic counterpart, the gravitational wave detection, which is pure physics, pure general relativity, gives you a distance, and the electromagnetic counterpart gives you a redshift, and you can construct this Hubble diagram in a very, very clean way. Ultimately, this method is basically, you know, limited by its absolute calibration, which is literally, you know, what is the actual power of the laser that LIGO is using, right? That is the limitation. That's an experimental thing that you can always improve. So, you know, we calculated that if we have 50 of these sources, out of which we've seen one, then we would be able to attain a % level precision on the measurement of the Hubble constant.
Oh, wow.
So, you know, the universe has to be kind to us and give us 50. Currently, in several years, we have one, so maybe we'll be waiting for a long time. But, you know, there are upgrades planned to LIGO, which is going to detect the gravitational wave side of things. And with Rubin, we can go and look for any electromagnetic counterparts, and we are ready on that side. And so over time, I'm sure there will be more of these sightings, and we will build up a sample of 50 of these sources, and we will be able to actually directly get a more physics-based measurement of the Hubble constant in the local universe. So I'm very excited for that prospect.
And you call it, as you made reference before, to standard candles, which are things by virtue of understanding their physics well. We know their intrinsic brightness, and therefore we can determine their distance by their apparent brightness. Use this term standard siren.
Sirens.
In this case, and I gather it's because the gravitational waves, we like to think about them as analogous more to sound waves than light waves, so to speak, and using them, you're saying you get a whole new way of judging distances, and in principle could get that Hubble parameter down so that we would know Whether
Yeah,
it's
absolutely. I think the phrase standard siren is actually a little bit of a misnomer. There's no sense of knowing an absolute siren and measuring an apparent siren. You literally do measure distances and redshifts. But I think it was originally come up with as a nice sounding phrase.
Yes.
I really,
I
it's very
liked it.
evocative.
Yeah,
Yes,
it's very poetic.
evocative.
I absolutely like
Yes.
that. So that's in the offing in principle. So you said you've got your first photons now down at the LSST. When does it become fully? Is it in the stage of getting to full operation right now?
Absolutely. So in July is the last thing I heard, is when the survey will start. So it's currently in the commissioning phase, and they're not really telling us the official, like how it's going story yet, but you just have to look at the faces of the people that are doing the commissioning, and they look very happy indeed.
Yeah, well, that's fantastic. And so back to the theory front. So we started, with this phenomenological model of cosmology, which had the 6 dials, the 6 parameters, dark matter being among them, dark energy being this other one that is directly relevant to when we're talking about the expansion of the universe. Where do you think we stand on theory in trying to?
Okay, so where do I stand on the theory is that when we discovered the accelerated expansion of the universe, one of the most stark things that came out of that was that we didn't understand the vacuum energy of space-time. There is a linkage between the so-called cosmological constant, which is the energy of empty space, which will make space-time accelerate in its expansion, and vacuum energy in a particle physics sense. So the second thing you can try to calculate by looking at all of the contributions to the vacuum energy that you get from the known aspects of the standard model of particle physics. And if you do that calculation, it's off by a huge amount. Some estimates are 10 to the power 60, some are 10 to the power 120, depending on various theoretical niggles that we won't go into. But it's a huge number that's off the actual measurement if you interpret the accelerated expansion as a cosmological constant or vacuum energy. So, for me, this problem, we all acknowledge, is given extra motivation by this cosmological observation of accelerated expansion, which is very secure. It's a very secure observation to the level that, it's received a Nobel Prize already. And I personally don't see very much theoretical development in trying to resolve this cosmological constant problem. Everybody can make the calculation and acknowledge it. And then I think, many theorists perhaps just kind of close their eyes and think, there's some symmetry that we don't know about that sets this to 0. It takes it from 10 to the 120 and sets it to 0. And the accelerated expansion we observe is, caused by some other particle we invented, or field we invented for that purpose, a scalar field perhaps, that gives a time-varying equation of state. And I'm afraid I don't like this way of reasoning. It's completely the opposite of the story we discussed about the dark matter, where there were fundamental compelling reasons for coming up with a dark matter candidate. It wasn't invented to fit a dark matter observation. Here we are doing the opposite thing. We're saying, here is a very, very fundamental problem. Let's just ignore it, park it, and invent a field that we say explains the accelerated expansion. So from the theory front, I think there hasn't been a huge amount of progress beyond that. The accelerated expansion observation was in 1998. That's the year I started my PhD. And we're still talking about a parameterization that was the so-called W0 WA parameterization that people invented back then to make sort of simple forecasting calculations. That's what we are still testing. It's just, a Taylor expansion. So this tells you that there hasn't been a theoretical, motivated kind of target that the observers have been set in order to go beyond this.
So I think the answer to this is obvious. In fact, maybe even the question you would say is not completely well formed. But early on I asked you, could you imagine an experiment or an observation that would convince you that dark matter is the wrong idea? And you pretty much said, not really. If we rule out WMAP, rule out AXIONS, then it'd be forced to, but it's not really where you imagine things going. When it comes to dark energy, if I was to say to you, can you imagine things developing in such a way that you would retire the word dark energy from your vocabulary? Is that something which you can imagine happening in the next
I
few
live
years?
in hope that we can retire the word dark energy and actually describe this phenomenon in terms of physics. I don't think the observation of the accelerated expansion as such will go away. So definitely that's very robust. And again, like the dark matter phenomenology, it's probed by multiple approaches now. And I think we will characterize the way the universe is accelerating in its expansion better and better over the next decade. We'll do that extremely well through multiple probes. But I guess you're asking, what is driving this phenomenon? And I think there, it's wide open. I don't back a horse here. I don't think there's a compelling theoretical idea. What I have been a bit frustrated about is that there's been very, very little attention paid to, what is the solution or resolution to the cosmological constant problem? And completely apart from my work in observational cosmology, I'm trying to, convene theorists in different scenarios to try to start motivating people to work on that. I can go into that if you wish, some strange ideas from condensed matter physics, but anyway, yes.
Well, I would like to go down that direction a little bit, because I think many of us agree that the dark energy mystery is far deeper than any of the other mysteries that really we've been talking about, because as you say, all it is right now truly is a parameter in an equation. I mean, you can take it to be Einstein's cosmological constant with just the value for lambda different from the one that Einstein put forward, right? So it's just a number in an equation. And you're also right in that when we try to do first principles calculations of what the amount of energy suffusing space should be, we get numbers that are radically different from what we know it to be from observation. So I think people at home should know it's not for want of trying of ideas. I mean, the cosmological constant problem, perhaps I should just say historically, long before it was agreed that it's a non-zero number, everybody thought, well, it has to be zero, or most people thought it had to be zero, and yet the calculations were yielding a number like 10 to the 120 or 10 to the 60, depending on how you parameterize things, a big difference from zero. And so for many decades, people came up with ideas for how you might get it to be exactly zero, through symmetry mechanisms and things of that sort. But in the end, none of it worked. So people have tried for decades, and then when the observation showed that it is non-zero, it was like, oh my God, now the problem's even worse now, right? Because now getting zero is a number we know how to get, right? Some kind of symmetry can set things zero. But getting a number that's decimal point 000, 120 zeros, depending on how you parameterize things, and a 1, now you're like, okay, I don't know what to do. And so people have thrown up their hands and gone in a direction that some consider non-scientific, some consider profound, which is this idea of a multiverse. And so if we could sort of go there a little bit, because that to me is the strongest motivation for not thinking the idea of a multiverse is totally nuts.
Yeah. You might know this. I don't think the idea of the multiverse is totally nuts. My motivation for thinking about the multiverse came from actually not the dark energy side, but literally, very early on in my career, being confronted with this observational evidence for superhorizon fluctuations, which led me to take the ideas of inflation seriously. And therefore, if you buy inflation, you have to buy eternal inflation.
So can you explain that point? Because that's a pretty important step.
Right. Yes, that's right. So if inflation is the explanation for the little perturbations we see in the cosmic microwave background, so if it generates structure through essentially quantum fluctuations in a scalar field. So a scalar field, we know of one scalar field in nature, the Higgs field is a scalar field. So that suggests that, the universe can have other scalar fields. So that doesn't necessarily strike me as a big extrapolation then. It is a type of fundamental component that the universe can make. So basically, if you have one of these scalar fields, it makes space expand very, very rapidly. But eventually, to make the universe like ours, this inflation of space, so this is called inflation, this accelerated expansion. And so we now think there's accelerated expansion in the early universe and in the late universe, but it is accelerated expansion. And this is not what's happening to the economy. We call it inflation, okay? So, hopefully, just like what will happen to the economy eventually, inflation has to end in the early universe. And then the standard, more sedate expansion of the universe that it's undergoing now can start. So the question is, does inflation stop everywhere? And in this picture, it seems very unlikely that it would. Inflation doesn't make a universe about as big as ours. It makes universes that are much, much bigger than ours. And also, there could be like a vast structure outside our observable volume where in some places inflation has stopped, and in other places space is still very expanding extremely accelerated rates in between. So these places where the expansion has stopped are like bubble universes, and we could be inside one of these bubbles, and there could be many other bubble universes. So this sounds like science fiction. However, you have to kind of stare this concept in the face if you buy that our universe had a phase of inflation in its very beginning, and that led to the origin of all the structure we see in it.
And let me give a quick, just to give
yes.
people at home a picture that I don't know if you like it or not, let me know.
Yeah.
But I like to think of it as the entire universe, or the big multiverse, if you will, is like a big block of expanding Swiss cheese, stretching Swiss cheese, with little holes that open up. And the little holes are universes like ours. And the cheesy part is that scalar field you were talking about,
That's
whose
right.
whose vacuum value, whose energy is pushing space to rapidly expand.
Yeah, that's a good analogy. But that cheese is then one time slice through this massive structure. I'm a huge fan of science fiction, but I'm an empirical scientist. So ever since confronting that picture early in my career, I've been trying to think of ways to test it. There is a very small window of opportunity by postulating that neighboring bubble universes could have collided in their early history. And that leaves potential signatures in the cosmic microwave background. We've looked for those signatures. It came up with inconclusive evidence. And that led me to
Hey, wait a second. So
yes.
you were actually on a paper early on. Am I wrong? You wrote a paper on this?
Yeah. So my team led that study.
Yeah, right. And so I've often made reference to that paper saying, there has been, a hint of a possibility, but, haven't really. So I'd forgotten that was you. That's great. and so where do we stand on that? Is there...
All right. So we haven't really changed very much in the observational picture since then. So when we studied the data from WMAP and Planck, we saw that there were 4 patches on the sky that were consistent with the expected signature of these cosmic bubble collisions. But the evidence wasn't high enough for us to claim anything. We came up with 2 ways to test this further. One is potential gravitational wave background from these bubble collisions, and one being we measured them in the temperature. Once you measure the temperature, the polarization signature that is predicted automatically is very specific. So those are 2 other ways we could have tested those patches to see whether we can increase the evidence. And then the limitation has been the technology. So there still aren't high fidelity enough polarization signatures over those patches that we can go and look in, although they're starting to be, and perhaps with Simon's Observatory, we will finally get that data. Since then, there's of course been this very interesting development of evidence for stochastic background of gravitational waves from pulsar timing arrays. So even the other possibility, which we thought was very futuristic, is coming into potential observational tests. But doing that analysis was what led me to understand that there were big theoretical uncertainties that were driving the low evidence. And one of those uncertainties is the rate of bubble collisions. Like, for example, if a bubble nucleates here, what's the likelihood that another one will nucleate right next to you? Is it just uniform, or is it increased probability that 2 bubbles nucleate next to each other?
And perhaps you should say they need to be nucleated close together, because if they're far apart, then they will be driven far apart by the exponential expansion of the space between them.
Indeed. Yeah, if they don't nucleate next to each other, as you say, the cheese in between is expanding extremely rapidly, so they'll be driven apart, so they'll never collide and you'll never get these signatures. So we have no theoretical tools currently, or we didn't at the time, to calculate whether there's an enhanced probability of 2 bubbles nucleating right next to each other. So this led me down a completely fascinating area of quantum simulators in the laboratory, which I can talk about briefly if you want.
Yeah, so is that something that you are doing now to try to...
Oh, absolutely, yes.
Okay, yeah, no, tell us for sure.
Yes.
But before you do, let me just quickly say, so that the
Yes.
audience doesn't lose track of the thread by which we happen to get here in this conversation.
Yes.
One utility of a multiverse is that you could imagine, and there are theoretical reasons for imagining this, that the amount of dark energy could vary widely from universe to universe, which means if you had a huge number of universes, there'd be a huge range of values for the dark energy within those universes, which would almost guarantee that there have to be a whole bunch of universes that have the tiny amount of dark energy that we witness. So that's where the multiverse has utility in trying to address the dark energy question. But of course, it has to be more than science fiction, as you're saying. And so
Yes.
let us know what you're doing in the laboratory to try to gain some insight into that question.
Before that, let me just add to your point there. I mean, I completely agree about this calculation where, there will be many universes where the dark energy value is low if this multiverse picture is correct. However, there's also the infamous anthropic principle that tells you that we are only likely to exist in universes where the dark energy value is low.
Yeah, that makes the argument even stronger, really.
Exactly,
Yeah, right,
exactly.
yeah,
That's
perfect,
right.
yeah.
But many physicists hate the anthropic principle. So that's why there's such a controversy about that explanation for dark energy. I mean, I take a very agnostic view on this because I'm an empirical scientist. I want to see observational evidence, and sometimes I think physicists make very strong statements about what can be true and what can not be true ever without very much other than an opinion behind it. So anyway, so
But
back
before you
to
go on,
yes.
I just want to emphasize, because that point
Yeah.
is so important, and I agree with it completely. So, sometimes I get hammered by people saying that, like I wrote a book on multiverse ideas, and I have
Yes.
spoken about them. They're in my
Yes.
NOVA program. Maybe we'll use some of the graphics when we, put this out on YouTube and so forth. And so people say, but that's so speculative. How could you, talk? Look, my view, I think like yours is, this is an interesting idea. It's far out. We don't know whether it's right or wrong, but until we can actually rule it out mathematically or observationally, allow us to explore it to see whether we can gain new insight, use it to solve problems, and like you're saying, maybe even get some potential evidence that it's real. You just can't rule out exotic ideas because they're too bizarre or too weird. So,
absolutely.
Yes.
I mean, that at some point, atoms was a speculation. At some point, exoplanets was a speculation. Now the search for life in the universe is a very mainstream activity, and it was done by crackpots, according to some people, even 20 years ago. So I really don't like this way of saying certain areas of investigation are too speculative to be allowed to even take place, even if it's just in people's brains. But anyway, indeed, let's try to kind of examine these theories and make them more rigorous, perhaps, and try to gain more theoretical insight, at least, to what they predict. So that's the motivation for our idea to actually simulate the false vacuum decay, which is the technical name given to this phenomenon of bubble nucleation, through simulating them. So this is essentially, okay, so when you put equations on a computer, you are not making a real universe, you're simulating a universe. It's very hard to do that for this phenomenon of false vacuum decay because it's a very non-linear, non-perturbative phenomenon of quantum field theory. And the mathematical techniques that we have to make predictions from it, for example, for the rate of bubble nucleation, assume certain symmetries, and outside those assumptions, you can't make calculations. So this mathematical formalism is called the instanton formalism. It simply doesn't have any view as to whether a bubble nucleates right next to one that's coming out, because it just pops into place. There's no real-time description for that popping into place. So what we want to do is to build a condensed matter system. This is actually an ultra-cold atom system where we can simulate a phase transition where if a certain set of experimental considerations hold, it's entirely analogous to the phenomenon of false vacuum decay in a Klein-Gordon model. And so this is an idea we've been developing for quite some time now, probably about 10 years. And it's developed to the stage that we have got very detailed understanding of those experimental conditions. And also a prototype experiment is being built in Cambridge in the laboratory of my collaborator Zoran Hadzibabich. So we can forward simulate this experiment just like we simulate theoretically cosmological observables. So from the perspective of actually doing the doing, even though this data is not like the data I study from the sky, the exercise we are doing is the same. We're forward simulating an experiment and we are comparing what the experiment actually measures with our simulations. And to do this, we came up with this semi-classical real-time picture of vacuum decay, which is basically based on putting all the quantum mechanics in the initial conditions and real-time simulating the evolution of the field through lattice simulations. Now, this is also a hypothesis, of course, that this semi-classical real-time picture is a good picture of vacuum decay. But what the experiment is doing is the full, quantum thing. So just seeing the match between the experiment and our simulations will tell us whether even the underlying assumptions are correct when we make these calculations. So it's not an empirical verification of the multiverse. It is rather becoming a better versed in building rigorous theories of force vacuum decay that help us understand the predictions of the multiverse.
And do you see a pathway to go from the results of that work to some probability framework for nucleating bubbles near one another, which is
absolutely. So we will be able. We already have some evidence from the semi-classical simulations that indeed there is an enhanced probability of bubble nucleations right next to each other, and we also have a kind of a qualitative physical understanding of why that happened. This has already been published, but the real deal will be seeing whether those experimental conditions that we can now implement will bear out these predictions that the rate of bubble nucleation gets enhanced when there's already one bubble that has formed in the experiment. So already there is that prediction that we now say through the semi-classical picture that there will be enhanced bubble nucleation next to each other. We also have other experimental observables that are not actually able to be calculated with instanton formalism. For example, we know that the precursor of these bubbles is a type of soliton. We can get that by stacking many versions of these nucleated bubbles and finding out the profile, and we definitely see this precursor. We could inject a precursor like that in the experimental side and see whether that causes a bubble to form. So the experimental control in these experiments is just astonishing, and so on. So there are already theoretical concepts and new tools that we have brought together, which didn't exist before we started talking about or thinking about these experiments.
Wow.
So it's a very exciting time.
Wow. That sounds really wonderful. I look forward to hearing the results of that, and frankly, of all the remarkable things that you're involved with. From the dark matter side, the particle physics version, the observational version. These issues of dark energy, inflationary cosmology, and doing this wonderful work in the laboratory that may ultimately give us some insight. So look, this has been a fascinating conversation. I want you to promise me that when you get the great data from the LSST, we can have you back on and give us an update on what you guys find. But until then, thank you so much for joining us. This has been great.
Thank you so much. It's been really fun to discuss all these topics with you, and great to see you again.
Great to see you. Bye.
Bye.